In mathematics, as well as in many related topics, the word function gets used sometimes interchangeably with expression, equation, anytime you have a collection of variables. It's important that we're really specific with what we mean by the word function. So let's get some vocabulary covered in 3.1 to help us be as specific as possible with our language. First vocabulary word, relation. A relation is any rule at all that assigns inputs to outputs. It's a pretty vague definition. Another vocabulary word that is related to relation is the word function. A function is a specific type of relation. It's a rule where each input is assigned only one output. So let's take a look at an example. For our first example, let's consider two relations. I would like the collection of inputs and outputs. Let's say that we have a collection, so we'll use some braces, and I'm going to use the notation that we usually use for relations where the input goes first and the output goes second. We call this ordered pair notation. A lot of times, you've probably seen this with an X, Y notation. So they don't have to be numbers. Let's say we use the relation that we're all really familiar with, grades and students. So let's say we have the input Jose gets an output of an A. And the input of Wu has an output of a B plus. And the input of Kiki has also an output of an A. Okay, so in this case, we have the input student and the output the grade. Definitely a relation, and this is also a function because every input has only one output. In other words, every student can have only one grade. I don't have a student that can have two different grades. So this is a function. Okay, now let's consider a different relation. Let's consider the relation where I list the grades and all the people who earned them. So the input is an A, Jose earned an A, who else earned an A? Kiki earned an A, and Wu earned a B plus. So I've changed my relation a little bit where I still have a rule that is assigning inputs to outputs, but in this case, this is not a function because I have an input that has more than one output. The input of the grade A has two different outputs. This is not a function because the input A has two different outputs. Okay, to be honest with you, you're not going to get problems that have grades and people. You're probably going to get a problem like this. -3, 7, 2, -5, and -3, 15. And you're going to be asked, is this a function? And what you want to look for is, do you have an input that has two different outputs? Definitely. We have the input -3. Remember, the input always goes first, and it has two different outputs. So this would be no. the input -3 has two outputs, 7 and 15. So it's not a function. Let's do a little bit more vocabulary so we can ask a more robust question. Let's discuss domain and range. The domain is simply the collection of all inputs, or x's, and the range is the collection of all outputs, or y values. So let's go back to examples similar to what we were just looking at. So let's consider the collection for the relation of ordered pairs 5, -3, the ordered pair 7, -3, and the ordered pair 0, 6. We're going to find the domain of the relation, the range of the relation, and is this a function or not? Okay, the domain is, remember, just the collection of all of the inputs, and we put the inputs in the first position. So this domain will be the collection of the numbers 5, 7, and 0, and since it's just a list, any order you like. Okay, the range is the collection of all of the outputs in any order. Now, when you're making a list, definitely include -3, but you do not need to include -3 twice, because when you're making a list, you don't need to include the same thing twice. So -3, don't need to include the second -3, because we're just making a list of all the numbers that are outputs, and 6. Cool. And is this a function? In other words, is there an input x that has two different outputs y? Okay, so the input 5 has an output -3, and I don't see any other 5s. The input 7 happens to have the same output, but we don't have anything here about an output having two different inputs. That must be okay. So 7 only has one output, -3, and 0 only has one output, 6. So yes, this is a function. Okay, so for the sake of comparison, right next to it, let's put another example. So let's look at the relation that consists of the collection of inputs and outputs 5, -3, 7, 2, and 5, 0. Now, relations can be any rules at all assigning inputs and outputs, and relations can have domains and ranges. So we'll answer these two questions first. So the domain of this function is just the inputs. So that would be, the domain of this relation is just the inputs. See, I use the word function. The input 5, the input 7, and I don't need to list the input 5 twice. So range then. Range would be the input -3, the output -3, the output 2, and the output 0. Okay. Function. Is this a function or not? So we need to find out the answer to this question. Is there an input x that has two different outputs y? Okay, so x equals 5 has an output -3. Oh no, x equals 5 has an output 0 also. So this would be no, it's not a function. X equals 5 has y equals -3 and y equals 0. So it's not a function. Basically, what you're looking for is repeated x values. Okay, let's do a couple more examples, and then we'll move on to formulas for functions. Okay, so let's look at the relation 3, -5, 2, -5, and 17, -5. Okay, so domain, let's see, domain is going to be the list of numbers 3, 2, and 17. And the range, the outputs, is just going to be -5. That's the only output that we have. Is this a function? So is there an x value? Is there an input that has more than one output? Okay, x equals 3. It only has one output, -5. Yeah, it has to share, but x equals 3 has just the one output. Same with x equals 2. It has only one output, -5. And same with x equals 17. It only has the one output. So is this a function? You bet. Yes. All of the x's have only one y. Okay, so let's compare that to the next example. Okay, so for this example, let's look at the relation consisting of the ordered pairs 3, -5, 3, 17, and 3, 0. Okay, well, the domain is rather boring. It's just the number 3. So it's just the number 3 for domain. The range would be the numbers -5, 17, and 0 in any order that you like. And is this a function? Is there an input that has more than one output? Heck yes, 3. 3 has -5 and 17 and 0. So is this a function? No way. X equals 3 has y equals -5 and 17 and 0, which is way too many. Okay, let's move on and start discussing domain for functions defined in formula form. So in this set of examples, we're going to still be finding domain, not the range, but the domain. But our formulas are going to be, or our functions rather, are going to be more of a formula rather than just a list of inputs and outputs. So I need to adjust my definition I gave you of what domain is. Domain is actually more specific than just the collection of all inputs. It's the collection of all possible inputs. And you might be asking yourself, well, what would an impossible input be? An impossible input, you already know. There are two big cardinal rules in algebra. We cannot divide by 0. And since we're dealing with real numbers, we cannot include negative numbers inside square root signs. So I'm going to write this in a math-English kind of combination. We can't divide by 0, and we can't have negatives inside square root signs. Those are the two things that we need to throw out as impossible x values. So looking over here at this example, when we find the domain, there are lots of possible x values. X equals 5, x equals 12, x equals pi, x equals 3/4, x equals 1. Oh my gosh, I'm not listing all of them. There's too many. So because there's too many to list, unlike the previous examples, in this we have an infinite number of x values. So the domain is infinite. So we need to write it as an interval. Infinite, by the way, doesn't necessarily mean there's the number infinity. If I were, just as an aside, if I were to list the interval of all numbers between 3 and 4, there are an infinite number of points in this interval. So we could have 3.1 and 3.2 and 3.3 and so on up to 3.9. Oh, I'm forgetting there's 3.101 and 3.201 and 3.30. Oh, and there's 3.111 and 3.222. And goodness, I could do this all day, literally forever and ever. So when we have an infinite number of x values, then we use interval notation to write them, but it doesn't necessarily mean we have to have infinity as one of our endpoints. So here's how we're going to write this. I would really like to write the domain of this as x can be any number except for 4. Because when x minus 4 equals 0, that would make our denominator equal to 0. So I'd like to say x cannot be equal to 4. That's in English. That's not an interval notation. So here's how you write x can be any number at all except 4. X can be any number smaller than 4, so negative infinity up to 4, with parentheses because I don't want to include 4, and x can be any number bigger than 4, so 4 to infinity with a union between it. So translating this into English, x can be any number that's smaller than 4, not equal to 4, combined with any number that's bigger than 4 but not equal to 4. Let's do another example to practice this. So let's find the domain of the function g of x equals x plus 1 over x squared minus 9. Now remember, when I'm finding domain, I'm kind of ignoring the numerator. The numerator can be anything at once. I just can't divide by 0. So let's see. In this case, there are 2 numbers that I can't have. I can't have x squared minus 9. X squared minus 9 can't be equal to 0 for our domain, which means that x minus 3, x plus 3 can't be equal to 0, so x can't be 3 and x can't be negative 3. Now, here's a suggestion for writing these where you want everything except for just 1 or 2 numbers. You want to do this. Write this on the number line. Graphing this on a number line is not required, but man, it really helps. And then I'm going to plot my 2 values that I want to toss, negative 3 and positive 3. And instead of putting open circles at those, which is what I would frequently like to do, to say I want this to be anything at all except not those 2 numbers, I'm going to put back-to-back parentheses at negative 3 and positive 3. So now my domain would be everything to the left of negative 3, skip negative 3, everything in between negative 3 and positive 3, skip positive 3, and everything bigger than positive 3. So I would write that negative infinity to negative 3 union, negative 3 to 3 union, 3 to infinity. And translating that into English one more time, x can be any number smaller than negative 3, skip negative 3. X can be any number between negative 3 and positive 3, skip positive 3. And then x can be any number bigger than 3. Okay, let's expand the types of functions that we're looking at with some different examples. So let's look at functions that have square roots. Discussing the function h of x is equal to the square root of 2x plus 10. We're going to find the domain. Since, again, this domain has an infinite number of x values that could be included to be okay in here to plug in, we're going to write it as an interval. And I want to remind you that we've got 2 things we're worried about for domain. We can't divide by 0. And we can't include any negative numbers inside square roots. In other words, only positive numbers inside our square roots. So when we're finding our domain for this function, we want to take the inside, it's called the radicand, 2x plus 10, and say that that function has to be positive, or it could be equal to 0. So I'm going to say 2x plus 10 has to be greater than 0 to make it positive, or it could be equal to 0. And then I just solve for x. So subtracting 10, I get 2x is greater than or equal to negative 10, which means x is greater than or equal to negative 5. And there are an infinite number of x's that fit that, so I would write negative 5 up to infinity. Cool. Okay, let's do another example. Let's find the domain of the function f of x equals 7 over 2x plus 10. So we have two problems here. We have a denominator, so we have to make sure that that denominator is not equal to 0, and we have a square root. So let's start writing our domain, where we state that the radicand, 2x plus 10, is positive. But I don't want to say that it could be equal to 0 because it comes from the denominator. I didn't have that problem over here. There wasn't a denominator besides 1. So over here, I'm actually going to erase. Whoa, that's too much erasing. I'm just going to erase the equals to part. So I have 2x plus 10 is just greater than 0 because it came from the denominator. Solving for x, I again get x is greater than negative 5. So this domain is parentheses negative 5 to infinity. And it has a parenthesis by the negative 5 because the square root of 2x plus 10 can't be equal to 0. It's in the denominator. Okay, let's try two more. Same set of directions. We're finding the domain, and we'll find the domain this time of the function named q of x equals the square root of x squared minus 16. Okay, so when we find the domain for this, no denominator, so we don't have to worry about that, but we want our radicand, what's inside the square root, to be bigger than or equal to 0. So x squared minus 16 is greater than or equal to 0. And I'm including the equals to this time because it's not from the denominator. Okay, here is why I covered section 5.5 right before I covered this. We need to know how to solve this nonlinear inequality. So this is a combination of the previous section and into this section we've got here. So we're going to factor it. X minus 4x plus 4 bigger than or equal to 0. So we have boundary points, x equals 4 and negative 4, which means we need to do a sign chart like in our previous homework section. So there's our number line. We're going to plot x equals negative 4 and positive 4. We're going to make columns, and we're going to pick values in each of these columns and see if we get true or false. So we might pick negative 100, plug it into our inequality, and we'll get negative 100 minus 4 is a negative. Negative 100 plus 4 is also negative, and yes, that is definitely bigger than or equal to 0. So our first is true. Our first interval is true. And if you remember, because we have odd exponents, this is going to alternate around all of our boundary points. So it should go true. If you picked 0, let's say, in here, you should get false. And if you pick something like positive 100 on the far right-hand column, you should get true again. So the columns that we want are always the true columns, which are the two outside ones. Means we would have for our answer, let me scooch this up just just a little bit, we would have for our answer negative infinity to negative 4. Ooh, would like a bracket because of the equal sign at negative 4. Union positive 4 to infinity with a bracket at positive 4 for the same reason. And what this means is, for domain, is we can pick any x value in this interval, set of intervals, and we plug it into Q of x, and we should get something that's perfectly acceptable as an output. Not error on our calculators. Okay, let's try one last example. So for this last example, I'm going to fit this right up here. I want to compare it to the previous example, so I would like to keep it on the same page. So I'll call this function p of x, which is equal to the 5th root of x squared minus 16. Now the 5th root is different than the square root because it's an odd root. It is perfectly okay to have negative numbers in a 5th root, in an odd root. So the domain for functions that have odd roots and no denominators would be all real numbers. Or maybe you write that negative infinity to positive infinity. Or maybe you write all real numbers as an extra bold R. But really, all those three things mean the same thing. X can be any number whatsoever. Most homework systems have negative infinity to positive infinity as their answer, but any version of that is fine. X can be any number at all. You can plug it in and out will pop a perfectly acceptable output.